For exam 3, we're going to cover first transformation of variables. When we try to fit a linear model to nonlinear data, one of the first go-to methods is to transform the variables to make the plot look more linear. So we're going to look at that today and a little bit next time as well. And then mostly we're going to spend time on something called logistic regression, which starts, that's part 8, and that starts on chapter 34. And so this next exam is only covering up to and including chapter 40. So it's really from 107 to 133, not as many pages. Okay, so we talked a lot about these assumptions, these 4 assumptions we need to fit a linear model, to use our usual t-tests and f-tests, or chi-square and z for large samples. And but what if you don't have, what if these a linear, what if you don't have data that it doesn't fit a linear model? What do you do? And what if the assumptions don't hold? So we're going to look today just at one of the go-to methods, which is just transforming the variables. The most common one that we're going to look at is a log transformation. That's what we're going to do today, especially because it's going to help us when we segue into our next section on logistic regression. This class has a huge spread in terms of how familiar people are with math. So for some of you, logarithms are probably just as simple as addition and subtraction, and for some of you, you're going to be really rusty on them, and you're going to forget even what they are. So hopefully I'll be able to hit a sweet spot and not go too slow or too fast. And if you need help at all, just come to office hours if you forget what logarithm, how to deal with them. Okay, so first off, remember these 4 assumptions: linearity, independence of the errors, equal variance, and normality of the errors. These 3 come up when we're doing inference, but sometimes we just want a more linear, we want to fit a linear model. It's simpler, and we have data that doesn't follow a linear pattern. So for example, so what am I talking about? Let's just work in 2 variables in the positive quadrant, positive x and positive y's, and just be real simple here. So you have this, ideally, we'd like a scatter plot to, let's say we have positive y and x, and we'd like it to follow some linear pattern like this. This is obviously, this data is obviously well fit by a line, right? And that's great, but often, so this is our ideal right here, but often we don't have a linear model like that. We don't have x and y's that follow a linear trend like that. And there's, often we have a curvilinear pattern. For example, what comes up in medicine all the time is a J-shaped curve like this, sort of like this. And for example, the x-axis could be something like drug dosage, how much of a drug is given. Let's say it was a chemotherapy drug, and you're trying to save somebody's life, so the y-axis could be death rate, mortality, right? That could be your y. Now, if you don't give the drug at all, you have a pretty high death rate, and an optimum amount of the drug works well, but too much of the drug can cause even more problems and more death, especially with something like chemotherapy, which attacks, is basically poison to a lot of cells in the body, not just cancer cells. So you might have something like this. Well, you could try to fit a curve to it, but often there's a transformation that's simpler to do rather than to fit a polynomial. And, but what's the problem? If you try to fit a linear regression model to it, it looks like this. And you can see that in the middle here, our predictions overestimate the death. I'd say it's way down here when it's actually pretty good in the middle. And on the ends, our predictions would underestimate how serious it is. So it's clearly not a good model unless we do some transformation of the data. Another type of curve that comes up a lot and would be something where the pattern maybe looks like it's as x increases, so does y for a while, but then it levels off. And a good example of this that you might not know about, but it's kind of a cool pattern, is if x is money, how much money you have, and y is happiness, how happy you are. Okay? Self-reported happiness, and also not only self-reported happiness, but measures of physical stress in your body, stress levels. And so that's your y. And you know it sharply increases in the beginning. If you have no money, it makes sense. Look, you have $0, you're homeless. Any little bit's going to make a big difference, and there's going to be a sharp rise. But then, after a while, it levels off. And the more, to the point where people keep thinking more money is going to make them happy, and it doesn't at all. So it's not at all a linear curve. And if you tried to fit a linear curve, a line to it, it's not a linear pattern. If you tried to fit a line for it, what would happen? At the ends, again, it would just give bigger errors in an opposite direction, depending if you're at the ends or in the middle. Okay, so that's the idea. And now you can look at this, and in these graphs, it's very obvious. But often what people do, and you've probably heard it if you take other classes, is examine the residual plots, right? How many people have said, oh, if you think some of the assumptions are violated, have you been told to examine something called residual plots, which are plots of the errors, the prediction errors, versus either the x or y variables? Raise your hand if you've heard that, or in classes where you do a lot of that. That's a go-to thing you'll see everywhere. If you go on in statistics and look at software packages, if you're trying to fit a linear model to make sure that all these assumptions are met, you look at residual plots. Well, just because it's easier to spot assumption violations doing that. Even at this level, even here, they're very easy to spot here. And the simplest type of residual plot would just be, this is ideal, these are bad, right? And we're going to have to do some transformations or something. But often what you do is look at the residual plots. So these are the actual plots, and the residual plots plot what? They plot, the simplest one is just to plot the x. So we'll have the same x down here, but instead of having a y, we'll have residuals. So this is the x, and these are the prediction errors here. So these are the residuals. So what does it do? So remember, the average of the residuals, when we fit this, is 0. So, for example, this would be a negative residual, so it would be down here. Let's say we had that's a positive one, it would be up here, and it just straightens. It's easy just because the slope, there's no slope, it's just flat, and you can see, you don't have to adjust for that. In this case, I'm sure that most of you can see that it would look pretty much, it's easy to examine either one, and it looks good either way. So that's what the residuals would look like. It's just getting rid of that slope and just saying, okay, the prediction errors you're just seeing how the prediction errors vary with x. And this one would look like what? I'm putting the scale here, I just had positive x and positive y, but remember, everything below the line has a negative residual, and everything above the line has a positive one. So you could probably imagine what this one would look like. It would follow the same pattern, it's just the slope is gone. So it's like pretty much just straightening it out. And you can look at these in our data program, and I'm sure you'll be doing some of this in the R as well. And if you take a course like 420, an applied upper level stats course, you're going to look at lots of different residual plots for violations of the assumptions before you proceed and try to build a linear model. All right, so that would be 0, and there's your residuals, and it's what you don't want. This is bad. You don't want a pattern, right? Check the scatter plot must show a linear trend, and the residual plot should appear as random scatter. This is not random scatter. It should just be, right? So this is okay, but you don't want to see any patterns in your errors because your errors are supposed to be random. That's the whole point, right? And they're supposed to follow independence equals spread and be normal looking. So we're going to go through this, and here, what would this one look like? Here are your residuals. Again, they're centered at 0, but now they're going to look like that. And it just tells you it's easier to read the residuals. If this is 0, well, you can just read what the number is across here, and you'll see what the residual is. Okay, so that's pretty much the idea. And now, so the errors in the true underlying regression model must be mutually independent. If we see a violation of that, it means we see clumps of errors grouped together, correlated with each other. And we don't want, like, just, knowing one violations of independence are very important, and they often indicate that you shouldn't be doing any type of any of these statistical tests because you might not have you're not modeling random variation. You might not have a random sample or a random assignment in an experiment to different groups. So independence is probably one of the most important violations to look for. And you'll see groupings. So the errors in the true, must be, check the scatter plot. It's basically the same thing. You don't want clumps together. That indicates that they're correlated, that errors are correlated. All right, so for example, something bad would look like, that's great, you don't see any clumps. But let's say you saw a whole bunch of clumping somewhere. Or here's a good example from our, we've seen ones like this, where you might have something like that. These are all grouped, and maybe these are all grouped. You have two different, this is an extreme example. And then you have this overall regression that's the opposite, and you have two separate groups here. This is X, and this is Y. And of course, the residual plot would be just very much the same. So here would be your scatter plot, and your residuals, I'll just put them right underneath. So this would be your residuals, your errors would look like what? The same kind of thing. But it doesn't have to be as extreme as that, but that's a good example. It could be, we'll look at some real life examples, and I think will help you understand this better. Now, what about equal variability? Equal variability comes up a lot in our Stat 100 data, and we're going to do I have an example in the notebook of it, and a square root transformation seemed to help, at least in that case, and often does. And the example in the Stat 100, I think, was in our notebook, I think, is drinking and partying from our real data, and you see there's some kind of fan-shaped pattern where there's way more spread, variability, way more spread as the partying and the drinking, that's what they get big. So around here, it's pretty narrow, and then you see this fan-shaped. And then you fit this linear regression, but it violates homoscedasticity, variability across the x's of the variability of the y's should be the same across all the x's. But look how variable those y's are. So for example, if people party 50 hours a week, some of them don't drink very much at all, and some of them drink a huge amount. Whereas down here, just the variability as you get to these high numbers for x and y is huge. All right, so this is bad. This would be a fan-shaped. This is, you don't want that. You want equal variability across, where it's about the same all the way across. So that's bad. Fan-shaped. And of course, the residual plot will look the same way. I don't think these are such great examples of the residual plot because they're so obvious to begin with, but actually it does help to look at the residual plots when things are more subtle. It's just easier to remove this slant. So that would indicate this. Violation of homoscedasticity. It's heterospread. Skedastic means spread. All right, and finally, and often we're gonna look at a classic example of that later on, probably next time. Now, normality of the errors. I said that this one, once the central limit theorem kicks in, if we have a huge sample, this one's not as important, but certainly with small samples, we have to, in order to use the t distribution to create confidence intervals for how, and to do our t-tests and so forth. Elliptical, nice shape, and follow a nice linear trend. So how can you tell if the errors are normal in something like that? How can you tell? Okay, what you want to check is within each vertical strip, do you have a little normal curve in there? So your residual plot, you don't usually check the residual plots. You do something else because it's hard to tell normality from a residual plot just from straightening this out. What am I even looking for? Maybe I could show you a bad one and you'll see. I'll do it here. What if it looked like this? You have you have linearity. But you have heavy, a lot of points out there, and very few points close to the regression line or something. All right? Now, whereas here, within every vertical strip, you should have every vertical strip of x versus y. These errors should be more tightly close. You have a lot more of them around the regression line where their value is 0 as a residual, right? And a lot less of them spread out. So you have an array of like little normal curves here. And I'm sorry I didn't draw it very well here, but let me show you the difference. Like here, do you see how that doesn't follow a normal curve? There's hardly any at 0, and they're really spread out. So what you do instead of like these residual plots is you do just a histogram. Remember, you want the errors to be normally distributed. So why not just look at a histogram of the errors? So this will be a histogram of the errors. Not how they change with x or y, but just a histogram. Because we're looking at all of them, and we want them, most of them, to be clustered around the line with small errors, right? In fact, we want about 68% of them to be within 1 standard deviation of the errors away, and just like 95% of them within 2 standard deviations of the errors away, and only like 5% of them way out here, very far away. So it would, and we want them to look like kind of like a normal curve. So with 0 right in the middle. That would be ideal when you look at a normal, but we don't want them skewed, and we don't want them, this plot, within any little plot, we have a histogram like this. We have it more like that. You see what I mean? We have a lot up there. It's symmetrical for this one, but it's not normal. I just drew an example. So like the residual, if you actually do a histogram of the errors, just a histogram of the errors, I don't have very many clustered there. So around 0, I don't have very many at all. So it looks more like, as we get further out, it looks more like that. Still, this particular one that I drew is still symmetrical, but it looks like that doesn't look normal. Or often they're skewed. So that's basically what you do. There's another graph that you've heard of, is where you take all these errors and plot their z-scores, the z-scores that they actually have in the plot, against the ideal z-scores if they followed a normal curve. And that's called, I think it's called a QQ plot. It's called different things. But it's basically what, if you ever see that, and this won't, this is just, I know people do it all the time, so it's not going to be on any exams or homework, but it would look like, and you see it all the time, it would look like what? It would look like you'd have a plot that was, how would it look? Basically, all right, I'm just going to try to draw it in a way that they usually are pictured. So it would be like you'd have 0, 1, 2, and 3. Most of the errors are there. -1, -2, -3. And this can either be the actual or the idealized. Depends on how people draw them. I'm wondering, I think usually, can't remember, but let's just say this was the, and then you'll have the same thing here. You'll have 1, 2, and 3, and -1, -2, and -3. And it doesn't really matter, but these would be the standardized, we can say ideal if errors for the normal curve, the z-scores, how the z-scores are distributed. Like, the standardized ideal z-scores. And then this is the actual standardized residuals. So it would be the standardized ideal residuals if they followed a perfect normal curve. I'm just showing you because it comes up a lot, and people in 420 were asking me about it, I think. So standardized residuals, if they followed a perfect normal curve, would be, and then what you want to see is what? If they followed there'd be a diagonal line. So the ideal would match up 1, 1, 2, 2, etc. But if there's curvature, if there's an S shape, or if there's curvature or something like that, then there's a problem. So sometimes there's like things that are just like that, or just weird stuff. And that would show that's a violation of normality. You'd want it completely lined up as much as you can, because then they'd be perfect, be normal. Okay, that's not going to be on the homework or exams. So far, that's pretty much a half hour on this, and there's so many courses that spend an enormous amount of time on this, because if these are violated, you can't use your standard tests, the F and the chi-squared and everything. We know that there's a lot of other stuff we can do, right, that I love doing, so it's kind of fun. We've already looked at some non-parametric tests we can do. We can do re-randomization tests. We can do simulations. But let's say we wanted to stick with these parametric tests, like the Z and the T and the F and the chi-squared. We want to do our regular linear models that assume all this. Well, what do? First thing you do is you try to transform the data to look more normal. So let's do that. So I wrote a little guideline for sort of a very basic way that people proceed. And don't take it as like written in stone. It depends on your problem and what you know, but just sort of a basic outline. And I'm not going to ask you to memorize it or anything like that, but just some guidelines to proceed. And so you see, if the scatter plot follows a nonlinear pattern, you see curvature. What do you want to do? I said, try following these basic 6 steps to make the plot linear and to make the errors around the regression line normal. All right, but you know, there's nothing written in stone. You can proceed lots of different ways, but this is a basic plan, simple. So you see some curvature there, and you want to still use a linear model. So you say, okay, I'm going to try transforming the y variable first. Why the y instead of the x? I'm just thinking that if you have multiple regression, you've got a lot of x's. And maybe just one y fix will do it for you. So you might as well just start with the one y. So you look at the histogram of the y, and if it's symmetrical, this is just a histogram of the y variable alone. Nothing to do, just look at the y variable and how it's distributed. And if it's symmetrical, and I forgot to let, and roughly normal, then just leave that variable alone. So if it looks like, you know, just roughly normal, it doesn't have to be, right? But often you'll see, particularly like with our data, like on our income data, right? It looks like a lot of our data is positive. So let's just look at positive y. So let's say we're trying to predict income. Well, our income data, I'll show you next time, and maybe do some problems next time on it because we have different data sets to look at this time. But it's enormously skewed. And the question I asked you was, how much money do you expect to make when 20 years down the road from now? And, you know, people, you know, there were a bunch of people, I can't even draw it on one graph. Because if I try to show, like people were saying around 100,000, or between 80 and 200,000, 50 and 200, I can't put the other people on the graph. I just can't. You can't put a graph. I can't even see the data that way. I can show it to you. So let's just take a less extreme example where you can, you know, something that's like right, this is tremendously skewed. So there's just like a huge, the extreme values are to the right. That's called right skewed. The extreme values are far away from where the bulk of the data is. So what do you want to do? You want to bring those in so we can put everybody on a scale to even see everybody, right? And we'll see an example of that. And so we take a square root, because if you think about it, square root of, for example, what? A square root of 25 would, or a square root of 4 would change somebody from 4 to 2. But then if you take a square root of 400, it would be a more drastic change. It would bring them all the way to 20. So square roots are the mildest way that we can bring this data in. A log would be is like an exponent. Think of a log. Let's say we're in base 10. So if you took the log of 100, that would be 2, and then the log of 1,000,000 would be 6. They wouldn't be so far apart, and 1,000,000,000 would be 9. It wouldn't be. Would bring those, and that's what we do mostly with income. You take logarithms. So if you need a more extreme, we're trying to make this look like this, right? And then if you really want to go extreme, but this is rarely used, because think about it, you're trying to get these big values brought in, but then you actually reverse the direction. So people do that. It's not as intuitive anymore, because now your biggest values, yeah, it gets compressed, but they also get flipped, and it's hard to interpret. But that's the idea. And if it's left skewed, you go the other direction, right? You increase these powers, or at least increasing from y squared to y cubed, right? You can think of this as, you know, y to the 1/2, and we're decreasing it, y to the -1, and some people think of this as y to the 0, even though it doesn't really fit, but you're decreasing. Okay, so let's go the other way, and this is how my exam scores are. And some people, I was trying to give, excuse me, They're still all positive. You don't have negative exam scores. But I was trying, look, when I give too easy an exam, look what happens. Everybody's all bunched up here, and you can't differentiate. And then you have this long left-hand tail, and everybody's all bunched up. And there's no way to tell these people apart as much. So sometimes people like to give just to get a better, clearer measurement, a harder exam, and then they can scale it if they want to change the grades at the end, but you can differentiate, because now these people are all bunched, and it's left skewed. The extreme values are here. So in order to distinguish these more, we'd have to spread them out this way, and that's why you would take the mildest would be squaring, then cubing, and then e to the y. Now, these are all for positive data. It's a little trickier for negative data, so let's not worry about that now. So then we look at what's the next step? We look at the scatter plot with the transformed y's against the regular x and see if it's linear. Sometimes that's all you have to do. If not, you go through the same process with the x variables and however many you have, one by one. All right, and then if the data is straight enough, you fit the regression, and then you find the residuals, and then you do all the residual plots, and you make a scatter plot of the residual against either x or the predicted values, and if you have lots of x's against each x. And this plot should have no pattern. If it shows a trend or a pattern, consider breaking the data up into groups. That's one thing that people do a lot. Like, look, we'll look at that later. There's two separate groups. Maybe we should split the data. But if everything looks good, then you plot a histogram of the errors and check that it's roughly normal. That's what we just did. So these are from the previous page. So let's just say as on previous page. No need to do it again. And then we're all set to go and make statistical inferences. Yay! And use the parametric tests. The usual one being the f-test and t's for the slopes. All right. So now let's do a fun example. I like looking at examples where you transform. You make these real life examples where the transformations really help you even see the data. And that's certainly true with anything about income, including our own data. But here's a cool one. When you look at body weight versus brain weight. So let's just go to our data program so you can play with this too. And well, this is where I got it from. So let's go to the right here, and I'll show you where to get it. Okay, so we're going to our data program, and then click Stat 100, because I think I used it in Stat 100 for something, and then look for 32 animals. And it's the average brain and body weights for 32 species of land animals, 8 dinosaurs and 24 mammals. So let's look at the scatter plot. And we want to say, let's say we want from body weight, let's say from your body weight, we want to predict brain weight. So this is for the average for each of the 32 species. So here's the body weight and here's the brain weight. And there, let's say if we try to fit a regression, it looks negative here. But can you see this doesn't, first of all, it doesn't look like there's 32. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't look like there's 32 here. You can't even distinguish these. You want to guess what this is? You want to guess what animal has a huge brain, a pretty big body too, but a huge brain compared to, what is that? The African elephant. Elephants are smart. They're really smart, sensitive. They're amazing creatures. Elephants, they're my favorites. I've never met an elephant, but I watch videos about them all the time. Never met an elephant, but there's so many good stories about them. Amazing. And this one's also an elephant, the Asian elephant. Now, here's another one that's big, way off the line. It looks like a different type of, and that is, you want to guess? With the big brain for the body? That's us, the average human. And then these giant ones are Brachiosaurus. All the way down, these are dinosaurs, all the way down to the little dinosaurs. Look at this one, Tyrannosaurus rex. That's a smart dinosaur. See, he's almost on the line. This one is pretty. Tyrannosaurus rex, and this is a Diplodocus, Stegosaurus. But now, who are all these little animals here? The cat, the monkey, the mouse. You can't even see them. They're all clumped together. Like even if I get rid, let's start over and try to identify who these are. That's a chimpanzee. That's a cow. The gray wolf, the cat, the mouse. But you can't see them. They're all stuck there. And there's no, look at the correlation. There's almost no correlation. What little there is. So what is the problem? Well, the problem is, let's look at this. Okay, notice how once you make this scale big enough to see the big animals and the big brains, the big bodies and the big brains, most of these points are just scrunched in there. You can hardly see them, and neither can the fitting program. It all looks like just one point, one big point. It's very hard to see that there's actually a lot of animals in there. You can hardly see them. And neither can the fitting program, which pays little attention to these little numbers. They're dominated by those big numbers. Yet that's where most, whoops, here, let me just go out a little bit. Yet that's where most of the animals are. That's where they are. And you can't even see them. They're not, the fitting program is not doing anything with them. You want a transform that counts these little animals just as much as the big ones. You care about these just as much as the big ones. So what do we need to do? We need to do some transformation that shrinks these in both directions. In log, it's going to be an extreme shrinkage to look at just the exponents, and then all the animals will show up. And it reminded me of one of my favorite stories from childhood called Horton Hears a Who. It's a Dr. Seuss book. If you haven't read it, I strongly recommend it. But it's about the Who's down in Whoville, who from the point of view of Horton is just they're on a speck of dust. They're just a speck of dust from big animals. And nobody's counting them. Their voices are not heard, and they're going to get destroyed. So this is a quote from the book. A person's a person, no matter how small. And so they didn't do a log transform in there, but they just made sure that all the Who's down in Whoville shouted at once. And I thought about it during the election, that if everybody voted and had their voices heard, and not just the big corporations dominating things, then we'd have a real democracy. So I just am trying to make you remember that what we're trying to do, we're trying to see everybody here. Okay, so is the scatter plot linear? No, it's not. So we transform the variables. So we're going to look at the histogram of the y's and then the x's, and they're here. We might as well just do it on the data program. And let's try it. Okay, and you can try it too. So what we're doing now is I'm just going to go to, okay, so I'm just going to go to the histograms. And what do I want to do? I'm going to try the y first. Do you remember the y is brain, right? So let's try that. And do you see now that it's right skewed? These extreme values are to the right. You can make more intervals here if you want. You can do as many intervals as you like here. But you can clearly see that in any type of interval, we've got right skew. So first, mildest, try the mildest first. Square root, big improvement, but this will be an even better improvement. Let's see. I want to make it look like 1, 2, 3, 4. I want to make it look like one in your notebook, so you can see. Yeah, that's what. It looks a lot better, a lot more. I mean, it's not perfect, but it's a lot better. So Let's just fill this in. So transform the variables. Now please look at, it's not symmetrical. Everybody gets that right on the exam, but people understand it, but they just forget the word for it. How are you going to remember it? It's right skewed. You look for the extreme values far away from most of the data. And if they're to the right, it's this. If they're to the left, it's left skewed. Okay? To make it more symmetrical, what are we going to do? Well, remember, the square root first, it's not as drastic a compression of those big values. So we'll try the square root of y, and it still didn't look quite, a huge improvement, but this is even better. And then you try the log. Now, in our program, it calls it the log of y, but it's actually doing the natural log, the log base e, and just writing it as log. All right? But a log base 10 would do the same transformation. It's just people prefer log base e. Log base 10 would be fine too. It's just this is more convenient for people, the log base e. Okay, so another way, the more natural way to write it as the natural n for natural logarithm, the log of y. But those are two of the same thing, and our data program doesn't put the e in. So don't mistake it for base 10 if you're worried about that. It's base e. Now, if the histogram were left skewed, what transformation would you have tried? Well, then we would have tried first. Now, we want to make those big values more spread out. They're the ones that are clumped together. So we want to do y squared, then y cubed, and then a really drastic one would be putting y in the exponent. That's not used nearly as much. All right, so let's move on, and so we look at the scatter plot with the trans. Now we have the log, Now we have the log of the brain weight. See, this is the data program says log, but this is the log of the brain weight. The data program writes log, but I'll just write here, data program writes log, but means log. Okay, log base e. All right, so we've got this, and it's kept the body weight, and now let's look at it. Let's see. Let's do it, and so we'll go back to the PC, and so now what are we going to do? Now we're going to go back. We've transformed it, and we want to do a scatter plot. So we'll do a scatter plot, and actually we'll have to, so we're going to do body weight and brain weight, but we haven't it doesn't hold that transformation. So the brain weight, we're going to do the log, and that's the picture that you see in your notebook. Now look, we can see all the animals. It's still not great, though. Look at the errors here. They're all in a line here. This is terrible. It's not a good linear plot, but at least we can see them now. It was the mouse, the hamster, the mole, the guinea pig. These are all these little rodents. The rabbit, very cute ones. The cat, the kangaroo, the gray wolf, and these are kind of et cetera, et cetera, et cetera, et cetera. So this isn't perfect. So what's our next step to do? And look, now we do have a slightly positive correlation, right? But it's not good, clearly. So what's our next step? Well, our next step is going to be to transform the x's as well. So let's do that just here. So, and see in this handy program, we can do that. We'll take the log of the x, and then it looks much better. And look how that r jumps up from like 0.1 to 0.65 almost. And now it looks pretty good. Still not perfect. You probably see grouping. You can see this grouping and that grouping, but it looks so much better. And you can look at the error plot, and you can see maybe this is a good case where you actually see more of the pattern, because you're not just sort of overwhelmed by that strong linear, slope there, that good slope, and you see that there really is a problem here that all these animals, this whole collection, is lower brains than you'd predict, right? And these have a trend too. So it's only like a few of them that, yeah. And those you want to get, you know who those are. Those are going to be what? The dinosaurs. Except for Tyrannosaurus rex. That's a smarter dinosaur. He's a predator with a small body, and he had to be smart to hunt. So he's got a little more brain there. Okay, so that's what this looks like. And for now, we could do a better job if we do what? Break them into two separate regressions. We'll do that later, but for now, let's just fit this. You see this equation? It's in logs. It says the log of the brain weight is equal to about 3 plus 3.2 times the log of the body weight. So let's just look at how to interpret that for now and do some predictions and confidence intervals, even though it's not completely kosher to do confidence intervals yet because we don't, it's not, if I did a normal probability plot, I guess I could show you that. I'd have to go to a different, to this regression, and then I'd choose the y variable, which is brain weight, and I want the log of that, and then the body weight is here. That's our x, and we have to transform that to a log, correct? How come I can't? Transform the x. Did I choose? I chose an x. What am I doing wrong? How about transform x? Oh, body weight. I have to choose it right here. It was just that. Okay, so now I chose it, and I can transform it. And we should get that same equation. We do. We don't get the plot because this is multiple regression here. So it's not showing you the scatter plot, but we have the same thing. We say that the log of the brain weight, right here is our y, is equal to, our intercept is about 3 plus about 0.32 times the log of the body weight. But I wanted to show you error plots because here you can see these, this is a histogram of the errors and it doesn't look quite normal yet. It will be better if we split up these two groups, like by adding a dinosaur. Does that look better? Yeah, that looks somewhat, that certainly looks better here, right? You don't see that pattern there. You see, there's always, with real data, you're not going to see this perfect normal curve and everything. Often people on tests just make up data. I hate to do that. I like to look at real data. But you can see that the errors look better here when we add dinosaur, but we probably would have to add an interaction term. There's a lot of different things we can do. But for now, let's go back to our document camera and do some of these problems. Let's not get ahead of ourselves. All right, so we transform the x as well and do the regression, and look. After taking the logs of both weights, we get a plot where all the animals show up. The fitting routine also sees all the points about equally. That's what we want. It comes up with a linear model for the logs with a decent R. Check that out. This R skyrocketed. Let me highlight it for you guys. Remember, it just zoomed up. You know, R is much better than it was before. It was about 0 before. And here's our equation. All right, so now what are we going to do? So now let's just make some predictions for log transformations. And I think I apologize if I go a little too slow because I know some of you are rusty with it. And I know some of you just are very, very used to it. But let's just it's going to be helpful because especially as we get into logistic regression to just get some of the basics down. All right, so here's the rounded regression equation. We have the log of the brain weight equals this intercept. This is what we've ended up with. Now, the body weight's in kilograms and the brain weight is in grams. Okay, some people might not like that so much, but it's not going to affect the slope. It wouldn't. Even if they're both in the same units, it would just affect the intercept. We'll see that later on. So don't worry about it. We'd still have just a same regression equation shifted. Okay, now let's use the equation to find the brain weight of a cat, of the average cat. Given that the cat, this is the average cat pictured on the plot. And we'll do the same with the human. And this is the one pictured in the plot too. An average is 62 kilograms, and that's the average cat. Okay, it's the one pictured in the plot. And so let's just predict, make a prediction using to find the brain weight of a cat given this, okay? And then we can check it on the plot and see, look at its residual compared to what we get. So let's find the log of this can only give us the log of the brain weight. So we get the log of the brain weight is equal to what? The intercept plus 0.32 times the log of this, of the body weight. Okay, and I got a calculator here. All right, so we can do this, and we can say 3 plus, I'm just doing that, 0.32 times the natural log right here of the body weight, which was 3.3. Right? What do I get? 3.382. Okay, might as well just leave all the digits in there. I'll just write it down like that, but might as well, because the next thing they asked us to do is to anti-log it to get the brain weight, to exponentiate it, anti-log it. So we just, just raise, take e to that power, e to that, and e to that, right? So we anti-log this, and we just get our brain weight. The brain weight equals, and then I'm just going to anti-log that. Exponentiate it. So I've got it in there already. So I'll just do the opposite. So I'll say second e to the x, second answer. And there's the brain weight, 29.43. This has no units. It's just an exponent. This has units. It's in grams. So that's 29.43 grams. So that's our answer. Now, the actual brain weight of the average cat here is 25.6 grams. So what's the residual? The residual is the actual minus the predicted. It's just your error. If you're above the line, it's positive. And if you're below, it's negative. So in this case, the actual is 25.6. So the cat is below the predicted. So it will have a negative residual of what? Negative 3.83 grams. All right. Now we can do the same thing for humans. So we'll do that. Exactly the same thing. Remember, you have to do it in 2 steps to get the actual brain weight. First, we're going to get the log of the brain weight. The log of the brain weight for the human, the average human, it says 3 plus 0.32 times the log of times the log of 62. So right here. So we can do that too. And we can say 3 plus 0.32 times the log of 62. And we get 4.32. And I'll leave it all in there, but I can write down 4.32. Now, on the data program, it will tell you if, it's very hard to code all this so that the tolerance, and if you use the answer that's given to you, like when you're doing these homework problems, just use the answer that's given to you, even if I hope it won't mark a more exact answer. This is wrong, but we'll give you a few tries if it does. Just whatever's given to you, once you code, you know what I mean? The answer that's up there, then use that, and you won't get things wrong due to rounding error. All right, so we just want to anti-log this. And what do we get? 75.239. All right, so 75.24, let's round it. So now we have the brain weight. All we did was raise both like that. And the brain weight is 75.24 grams. Okay, now look at this. The actual human's brain is huge. way bigger than that. So there's a giant residual, and that's why the human's way off the regression line compared to the cat, right? So the actual minus the predicted is equal to, look at that residual. In grams, the plot showed it in logs, but it was a big difference. All right, now you can see, if we go here, this actually, whoa, I can't remember which is which. I think this, yeah, this is the human predicted to have a log around here. Instead, look at this. And the cat is just a tad off the line. So it did a great job for the cat, but terrible job for the human. We're going to improve on that when we split into two groups, dinos and mammals. But for now, let's just do this. Okay, so now what do we have? We have this log. A lot of people don't like log equations because they want to, it's more intuitive to turn it back into the terms of the brain weight. It's more intuitive to predict brain weight rather than log of brain weight. So what are we going to do here? So basically, this is the general picture of what happens is that the intercept and the slope in the log equation become exponents once you transform back, because logs are exponents. So that's what it's going to look like, the form of it, and you can see. So, so what do we have? We have the log of the brain weight is equal to 3. So this intercept will become an exponent. It will be e to the 3. See? And our slope, which is 0.32 times the log of the body weight. This slope will be log of body weight raised to the 0 point, will appear up there. So let's do it. You'll see it. This is body. BD, body, sorry. That's the abbreviation, and BR is brain. Okay, so now we're going to exponentiate both sides. Raise both e to the, take this, raised e to that power. And here we get, obviously, we're anti-logging it. We get the brain of the weight, brain weight, brain of the weight, right? Like your weight has a brain. What am I saying? Brain weight, okay? And then we get e to the 3 plus 0.32 log of the body weight. And this is going to simplify, you'll see in a minute, to what? Well, exponents addition, you know that. You know that. That's just going to change to multiplication. Let's simplify it. And then it's going to be e to this. That's a product, so it's commutative. Why don't I write it this way? Log of body weight. It's body weight. Log of body weight. I'm just changing it like that, times 0.32. That's a times. And I'm doing that because you can see this part is just anti-logging a log, so we're just going to get body weight here. So we end up with e cubed times the body weight raised to the 0.32. Just like I said. So let's take some highlighter here. And I'll make it pink. So what am I saying here? I'm saying that this slope right here becomes, in the log equation, is going to become the exponent of the x of body weight right here. That's the key feature. That's what it says right here. See? So this and this become exponents. And here they are as exponents. But this is the important exponent because this is your x variable. So it's your x variable. So when you transform it back, you get this equation. All right, any questions on that? So here, these both become exponents. This becomes e to the cubed, and this becomes at your x variable to the 0.32. So this idea is the same. Let's see. Do you want me to do this part? What if we had taken a log base 10 instead? How would that change things? It would do, I mean, I think you can see that it wouldn't change the slope. It would just change the intercept. And same if we just multiplied, because okay, so we can do this. It will just take us a second. We just have to transfer. What if we had taken, so what if we wanted to do instead of the log, natural log of the brain weight? We have this equation. We just want to change it to the log base 10 of the body weight. So, do you know how to do that change of base? If you want to change from a natural log to a log base 10 of the brain weight, you have to divide by 2.303. E to the 2.303, I think, is 10. So you have to divide by that. So you have to divide both sides by 2.303. I just know that. That's hard to say. Oh, where should I put that? I'll put it right here. I'm using this, that the log base 10 of x is the same as the log of x divided by 2.303. That's all I'm doing there. Okay, so I divide both sides by 2.303. And if I divide this whole side by 2.303, I'll get 3 divided by 2.303, which changes your intercept. But does it change this? No, because when I divide this whole thing by 2.303, I get the log base 10 of body weight. So it's just plus 0.32 times the log base 10 of body weight. So the point is that this slope remains constant. That's what I'm trying to show you. Even with the change of base, and it would be the same if we changed to kilograms put it all in kilograms or all in grams, because we'd just be multiplying both sides by some constant. All right. Or one side we'd be multiplying by that. One side, it would still just change the intercept. Okay, any questions? Now, let's progress. I said I would let you out a little bit early, so let's just do this last page. And computing confidence intervals for transformed variables. What you're going to notice when you do this is you're going to get something called asymmetrical confidence intervals around your original variable. Why? Computing confidence intervals for transformed variables. We transform the variables in order to get the errors around the regression line to be about normal. This means that we can use that standard deviation of the errors to compute confidence intervals for the transformed variables, not for our regular variables, not for our original variables. We'll have to do it for the logs, that's right. And then we have to translate those confidence intervals back to the original variables. So it's a two-step process. So how do we then translate the confidence intervals back to the original? So we do it in two steps. So we do the confidence intervals the usual way. Let's use the normal curve to make the calculation simpler so we can focus on this new idea of transformed variables. So we are assuming our assumptions are met. And you know they're not quite met yet, but we're assuming assumptions met. All right. We really need normality met here because we don't have such a big sample size and we don't have it yet, but let's pretend we did. So we're doing our usual thing with the confidence intervals. Like a 68% confidence interval is following the normal curve is going to be plus or minus 1 standard error on the normal, if they followed the normal curve. Then between 1 and negative 1 is 68%, and between 2 and negative 2 is 95%. I'm just approximating. So this will be 1, and the 95% will be plus or minus, zeros in the middle. 2 standard errors. It's really 1.96, and if we were really doing the t-curve, it would be different. Okay, so now we want to translate the endpoints of the confidence interval back. So we're going to be using this for our confidence intervals on the log. So let's go back. We estimated the brain weight. We have to do it on the log. Okay, what did we estimate the cat brain? The log of is this the cat? What are we doing here? Cat. Yeah. So we did it before. We said the log of the brain weight, just to refresh your memory, is equal to 3 plus 0.32 times the log of 3.3. And we got 3.382. Okay, that's what we have. And then we estimated the brain weight from that to be what? We said the brain weight then is equal to e to the 3.382, and that's where we got 29.43. That's from the previous page. All right, so now we really want confidence intervals around that, but the standard deviation for the errors that we're using, which was given to us, where is it now? It's on the previous page. Where do I have it? Here, right here. This is in logs. That was done for the logs. So this is what we have to use. This is what's normally distributed. This is what we have to use. I mean, this is what the errors are normally distributed, and this is a measure of their standard deviation. Okay, but remember, it's for the log of the brain weight. So we have to do a 95% confidence interval has to be in the form of the estimate. It has to be for the log of the brain weight. So it has to be the estimated log of the brain weight, which we have right here, that 3.382, plus or minus a critical value, z, associated with 95%. So that's 2 times our errors, times 1.6. So that's 3.382 plus or minus 3.2, right? So we have 3.382, we'll put the lower one first, minus 3.2 up to 3.382 plus 3.2. And that's the endpoints. That's our 95% confidence that the log, the true log, is within all of the true log of the cat's brain weight is between those limits. So those limits are 0.182 in logs to 6.582 in logs. But that's not what we're interested in. Now, if we want for the brain weight, what do? Well, we just anti-log those two. So all we have to do is just anti-log those. So we'll say, instead of those, we'll write what? E to the 0.182 to e to the 0.582. And then we'll get our new limits. And this is for the brain weight, so we get 1.2 to look at this, approximately 722. So this is a confidence interval for 29.43. So you can see we don't have we have an asymmetrical confidence interval. Note, we don't have 29.43 plus and minus something. We don't have an arithmetic mean here. We don't. We have the log is an arithmetic mean, but this, we don't have. The confidence interval is symmetrical for the log of brain weight. We have instead 3.382 plus or minus what? 3.2. So this is the arithmetic mean, the log, the estimated log, but the other one's not. So do you know what it would be? It's not the arithmetic mean, but it's the geometric mean. The geometric mean. So what that means, if you want to check it, It's the geometric mean, so you would check that 29.43 isn't in the middle, isn't the mean of two numbers, but it's the square root of their product. So check that to make sure you've got the right thing. And you probably can see why, because remember, 29.43, we have it right here, is that, because this is e to the 3.382. And let's do both of these. 1.2 is what? 1.2 is e, how did we get it? How did we get the 1.2? We said e to the, that 0.182 is this, right? E to the 3.382 minus 3.2 times e to the 3.382 plus 3.2. And you can see when you multiply these two together, this is going to cancel out, right? That's gone. And all we have is the square root of our, all we have is our estimated cat's brain weight is the square root of e to the 3.3. It's a, it's just always a true statement. So it's useful to remember that when you compute the confidence intervals, you're looking for, it's not a plus or minus, it's not going to be in the middle, it's asymmetrical. So whenever you're doing these log transforms or any square root transforms, you don't have those symmetrical confidence intervals around your original variables. So, okay, so if you have any questions on your own, your homework's posted, and we'll finish this up next time and move on to logistic regression.